This is video number 9 for the assembly programming and reverse engineering course. And in this video, we will talk about the last calling convention example, and that is this one. M64, that's a 64-bit packed value. M128, that's a 128-bit packed value. Struct, that stands for structure. Float, yeah, we know that already. And here are the values that are saved on the stack. And at first now we'll show what the program is doing. Here we can now see the output 5.0 and 6.7, and this is the result of a 2D vector calculation. Then we have the output 2.2, 3.3, 4.4 and 5.5, but before I can talk about the source code, we need to cover some things at first. At first we need to talk about 2D vector calculations, and here's an example how to add two vectors. So this is the first vector, vec1. It's holding the value 1.5 and 2.5. So in total it's holding 2 quad words and therefore 128 bits. One quad word is equal to 64 bits. Here's the next vector, and now we can add these two vectors. So at first we need to calculate 1.5 plus 3.5. That's 5.0, then 2.5 plus 4.2 is x, and that is 6.7, and that is then the result of the vector calculation. And this is also what we have seen here already in the output. Okay, then packed values. What are packed values? Packed values are multiply smaller values in a single register or in memory. And this is how that looks like in memory. So this is the memory address of vec1 in this example, and this one 1.5, this is how it looks like in hex, and 2.5, this is how it looks like in hex. And now we need to read the numbers from right to left, so in little endian format. Then we have the XMM register, that's a 128-bit register, and we know already one vector has a size of 64-bit. And in this example here, this is one 64-bit value. This is a 64-bit value, and then we can see that we can save two values, two 64-bit values in the XMM register. And here we can see so the 2.5 and the hex value, and here's 1.5 and the hex value. But we can also save more than just two values in this example in a 128-bit register. But yeah, of course, then we can't use a quad word, but yeah, then we can use a D word, for example, and then we would be able to save 4 D words in one single register. Then we can talk about packed values, and packed values that are multiply smaller values in a single register or in memory. And here we have our vector, and this is a memory address of vec1 for this example. And this is how the value 1.5 looks like in hex in memory. And here's the value 2.5. And now we need to read these values from right to left, because in the x86-64 architecture, Intel and AMD CPUs, they are using the little endian byte order. And yeah, that means that values in memory, they will start with the least significant byte. And here's a simple example. Let's say we have a variable number D word, so 32-bit, 0x1, 2, 3, 4, 5, 6, 7, 8, and the 1, that is the most significant byte, and the 8, that's the least significant byte. And then in memory it would look like this: 7, 8, 5, 6, 3, 4, 1, 2. And yeah, that is how that works. And then we have here the XMM register, and that's a 128-bit register. And we can already see here we have the vector, and in the vector we have two quad words. So each Each value has a size of 64-bit. And here's the first one, so 2.5, 1.5, and yeah, we have now saved two values in one register. But yeah, we can also save more than just two values, but then of course no what words, but for example D word, that we could save 4 D words in a 128-bit register. Then we can talk about how to move a packed value in an XMM register, and for that we're going to use the vMoveUPD instruction, and the V, that stands for WAX 128.66 UF-WIC, and then moveUPD, that stands for move underline packed double precision floating point values, and the vMoveUPD instruction, that is then the instruction that we are going to use to move the values from our vector into an XMM register. And vMoveUPD, that works also if the memory addresses of our vector is not aligned, but yeah, that can cost performance, but it will not lead to a serious problem. So the program will not crash or something. And yeah, if the memory addresses are not aligned, then that can lead to cache line splits penalties. But I will not talk about memory alignment or cache line splits in this video. That's maybe something for another video. But yeah, if someone is interested here in the documentation, some information about that can be found on page 133. So go to this website here, then select here the latest version, and from here you can download the document or just browse through the through this PDF document. And here are some documents that are a little bit older. So yeah, here just select the latest version and then use this download button. Then we can talk about the allowed vMoveUPD combinations, and here are the combinations. So we can move the data from a memory address into a register, or from a register into a memory address, or from a register into another register. Then we can talk about the vector calculations, and to calculate the vector we are going to use the v@pd instruction, and the v that stands then for WAX 128.66 UF-WIC58, and that is a encoding. And @pd, that stands for packed double precision floating point values. But there's also a @pd instruction without the WAX encoding, and then it's just called @pd. And if we are going to use the @pd instruction, then here in this example we will overwrite the value in XMM0. So we move the data from WAC1 to XMM0, then from WAC2 to XMM1, and then here we calculate the vector. So XMM0 equal XMM0 plus XMM1, and then we can already see that we will save the result in XMM0, and then we will overwrite the value that we have written previously into XMM0. And if we want to avoid that, then we can use the v@pd instruction. That is using the WAX encoding then. So in this example, we move the data from WAC1 to XMM0, then from WAC2 into XMM1. And here we can see now the calculation is then XMM2 equal XMM1 plus XMM0. And yeah, the @pd, and yeah, and the result goes to XMM2. And yeah, so the @pd instruction that is using the mod rm encoding, and therefore there's only space for one destination and one source register. And then when we take a look at the v@pd instruction with the WAX encoding, then we can see that we can have here one destination register and two source registers, and therefore we are not we will not overwrite here any values that we have written previously into XMM1 or XMM0. And here are the allowed v@pd instructions. So we can use a destination. We can use a destination register. We can use a source register, and we can use another source register. And this is also allowed. destination register, destination source, and a memory address as a source. And yeah, that are also allowed combinations for that. Don't mix SSE instructions with AVX instructions. SSE, that stands for Streaming SIMD, and AVX, that stands for Advanced Vector Extensions, and AVX, that is a successor of SSE. And I will not talk about the details here. That's also something for another video. So for now, just keep this in mind. Don't mix SSE instructions with AVX instructions. And here's an example. Move UPD, that's the SSE instruction, and VAdd PD, that's the AVX instruction. And if we mix these instructions, then this can lead to problems like transition penalties. Here's a better solution. Move UPD, that's the SSE instruction, and add PD, that's also a SSE instruction. But yeah, move UPD and add PD, they are limited to 128-bit register. Here's a better solution. Just use vmove UPD, that's the AVX instruction, and vadd PD, that's also a AVX instruction. And vadd PD and vmove UPD, they support 128, 256, and 512-bit register. And here's an example how to use vmove UPD and vadd PD on a 512-bit register. And then here in this interlink, you can find this document. And then on page 1411, we can see move UPD, that's the SSE instruction, and vmove UPD, that's the AVX instruction. And then on page 720, add PD, that's the SSE instruction, vadd PD, that's the AVX instruction. Then we can talk about the source code, and here this is the script that I'm going to use to assemble the program. And here is the first vector, this is the second vector, and we add these two vectors, and then we will see the result. And the program, it will also print the vector 3 and vector 4. So this is the result of the vector calculation, so vector 1 plus vector 2, and we can see here the result 5 and 6.7, and then the program prints the value 2.2, 3.3, 4.4, and 5.5. And then here we have the result variable, so resq2, and that means that will reserve two 64-bit values. So in total, this is then able to hold a 128-bit number. The stack alignment, at first we reserve 8 bytes for the stack alignments and 32 byte for printf, then 8 byte for the first parameter on the stack, and then another 8 byte for the second parameter on the stack, and then total we get 56 bytes that we need to reserve. And here we move the data from VAC1 to XMM0, then from VAC2 to XMM1, and then we calculate the vector. The result is in XMM2. Then remove the result from XMM2 to result, and then here we load the format variable so the address of the format variable to RCX, and this will print the vector result. So for the first number, this is the second number, and this will print the value 2.2, then 3.3, 4.4, and finally 5.5. And here's the null terminator. Okay, and where are we now? Okay, here. And here now we move the calculated result to RDX. And here again, I've talked about this already, but if someone does not know why we're doing this, so move the value of RDX in the corresponding floating point register. XMM1 is volatile, so we're not violating the calling convention. And yeah, if you don't know anymore what that means, then watch the second part of my calling convention video. And start at 53 minutes and 45 seconds, and then just watch it until the end. That's just a couple of minutes, and then you know what it means if we move a value into a corresponding floating point register. Okay, here we can see the second result from our calculation. So the first result is as a variable result, and then we need to increase that by 8 bytes, and then we point to the second result. So this is result, and this is result plus 8, and yeah, why plus 8? Because 8 that's 8, that means 8 bytes, and 8 bytes that's 64 bit, and we know already here, and we have reserved in total 2 quad words, so 2 64-bit values, and that means 2 8-byte values. Okay, and then we move the data from the second result to the corresponding register. That is in this case now XMM2. Then we print vector 3, or don't print it here, but we move the data from WAC3 to R9, and then from R9 to the corresponding floating point register, and then here WAC3 plus 8, because then we want to copy this value to R10, and then we store that on the stack. And then the number 4, so the first vector 4, then we move again the data from vector 4 to R10, and then from R10 to the stack, and then finally the last number, so that's back 4 plus 8, and back to R10, and then from R10 onto the stack. And yeah, R10 is that's a volatile register, so you can use that as a scratch or a temporary register, but I've talked also about that in this video, on the calling convention part 2 video. And then finally we call printf to print the result on the screen. Then we can take a look at the disassembled program. And here we see now the code of the CRT. So now we can click on memory map, then look for the name of the file that we have disassembled. So in my case, it's file.exe. And here we can see it file.exe, and then we can double click the text section. Or if we click here on CPU, and if we just scroll up through all the CRT code, and then on the top we can see our own code. And I've set here already a breakpoint, so we just run the program now. And then we are here sub RSP 56 and 38 in hex, that's 56 in decimal. So here we will reserve the memory on the stack, and then we will move the data from WAC1 to XMM0, so use XMM0. And now we can see the data. Here's 1.5, here's 2.5, and here are the hex values. And then remove the data from WAC2 to XMM1. And here we can see the value of 3.5 and 4.2. And then in the next instruction we execute this, so this one, v add pd xmm2 xmm0 xmm1, and here we will calculate the vector, and the result goes to xmm2, and we can then also see that we are not changing the values in xmm0 and xmm1. And here's the result, 5 and 6.7. And then remove the result from this calculation into our result variable. And here we can see it's 0. And now when I execute this instruction, then remove the data from xmm2 into our result variable, and here we can see the data. Then in the next instruction we move the address of the format value of the address of the format variable into RCX, and RCX, that's now holding the address of our format variable, and then remove the RDX register to remove the result from our result variable, or the value from the result variable to RDX. You can see that is the first value, and then remove this value to xmm1. And now, of course, we will override the value here in xmm1, and then we can see the value 5. And here that is the first value. And the next instruction, then we will move the second value from the result variable to R8. So here result plus 8, and we move all that to the R8 variable. So R8 is now holding the value. That's the 6.7, and then remove that from R8 to xmm2. Here's xmm2, and then we can see the second result of the vector calculation. And then in the next step, we remove the data from vec3 to R9, and here is now R9, and that's in the value 2.2. Then remove that to xmm3, and here's xmm3, and you can see the value 2.2. And then remove the data from the second value of the vec3 variable to R10. So we are here then, move R10, vec3 plus 8, that goes to R10. You can see it here in the R10 register, and then remove it from R10 to RSP plus 20. And if we want to see these values, okay, so first I will execute this. So now we can click here on the stack, hold Control, press G, and then type RSP plus 20. And here we can see the value in hex. And we can also click here in the hex dump, hold Control, press G, then type RSP plus 20. And we can also change the view here, for example, to double, and then we can see here the value 3.3. But yeah, for now we'll just keep the hex view here. Okay, then that was the value 3.3. Okay, then we are here now vec4, and now remove the data from vec4 to R10. And here we see the value, and then remove that also on the stack to RSP plus 40. Okay, so RSP. Okay, in this case, yeah, we need to type the hex value, so that's in 28. And then we can see here the value. And then remove the data from vec4 plus 8 to R10. And then from R10 again on the stack, and so on. And then we call the printf function. Yeah, that's what to printf then. And where's the program? Here it is. And now I will use the jump with the step over button. And here we can see the result. And yeah, here this is not showing the call to the printf function, but there are plugins that we can use, but that's also something for another video. And yes, then we can go to the next example. Then we can talk about this example. And here we add also two vectors and then print the result on the screen. And yeah, vec1 has now a total size of 64-bit, and vec2 has also a total size of 64-bit. And here DD, that stands for D word, so this is one D word. This is also one D word, and one D word is equal 32 bits. And yeah, 32-bit times 2, that's then 64-bit. And then later we save the result of the vector calculation in this result variable, and this variable that has space for 2 word words, so in total 128 bits. And we can again use this script here to assemble the program. But I've assembled the program already, and I've loaded also an x64 dbg. So the first instruction that we're going to execute is this one, sub RSP 28, and 28, this is a hex value, and decimal, that is 40. So now we reserve the memory, then remove the data from WAC1 to XMM0. And here we can see the vector 1.5 and the value 2.5. Then remove the data from WAC2 to XMM1. And here are the values 3.1 and 4.1. And then we need to add these two vectors. So in order to do that, we execute the add PS instruction, and add PS, that stands for add packed single precision floating point values. And here the formula is xmm0 equal xmm0 plus xmm1. And yeah, the result goes to xmm0. So this is how it looks currently. Now I execute the instruction, and then here we can see the result 4.6 and 6.6. And now what we need to do is we need to convert, or we need to promote this vector from 64-bit into a 128-bit vector, because this is still a 32-bit value, and this is also still a 32-bit value. And we know already that printf works only with floating, with double precision floating point numbers, and therefore we need to promote the vector. And in order to do that, we use a cvt-ps2pd instruction, and that stands then for convert packed single precision floating point values to packed double precision floating point. And yeah, source and destination register, they are equal. So now pay attention to xmm0. This is how it looks currently. Now we convert, or now we can promote the vector, and here we can see the new result. But instead of 4.6, we see now 4.5999, and instead of 6.6, we see 6.599, and that is because after the conversion, it's not possible to print these values or to represent these values exactly in binary, and therefore we see here these rounded numbers. But printf, it will then round it to 4.6 and here to 6.6. Okay, and then remove the then we're here, and then remove the data from the result from the vector calculation into our result variable. And here's the variable, so it's still empty. And now we can see here the data in hex. Then remove the value from the format, or remove the address from the format variable to RCX. And here's RCX. And you can see now, it points to the address of the format variable. And then remove the data from, then we're here, remove the result to XMM1. Okay, now where's XMM1? Here this is how it looks currently. And now remove the data to XMM1, so the result from the vector calculation. And then here we can see there's a result again. And then remove the result into the corresponding general purpose register. And then from XMM1 to XMM2. And then we need to unpack the value. So, and in order to do that, we execute the unpack and interleave high packed double precision floating point values instruction. And that's this one, unpckhpd. And what this is doing, Now pay attention to this value. No, to this one, because this is the high part, this is the low part. So this one is this hex. So for example, I can also just add a 7, for example, then we can see that only the upper numbers are changing. Okay, so now we move the high part into the low part. That means this value goes into the low part of the XMM2 register. And we do that because later we move then the low part. So we use move Q, and move Q then moves the low part of the XMM2 register to R8. And yeah, now take a look at XMM2. So here it's 4.599, and now I will execute the conversion or the unpack instruction. And now we can see that that we also have here the same value. And then remove finally the data to R8, and then we can print the result on the screen. And yeah, here's the result of the calculation. And then we can go to the next example. Then we can talk about the last code example, and in this example we will pass a structure to a function. So here struct, that means structure, and C in this example, this is the name of the structure. And this is a program, and this program, it will read the current cursor position, and then it will print the position on the screen. And in order to do that, we will use the GetCursorPos function from the Windows API. So just go to Google, type mstn GetCursorPos, and then you can find an explanation to the function. And GetCursorPos, that's the function from the user32 DLL, and that means that we need to link against the user32 lib. And therefore we need to adjust the script that we use to assemble our files. And okay, so it's kernel 32 lib, that's not needed here, but it's also no problem when it's in the code. So then we can just type user32.lib, and then we can save the file, but don't do this, so don't append that at the end. If you now save this file, and then if you would try to assemble the program, that would lead to an error message. Okay, then we can keep talking about the function. So here's the function name, GetCursorPos, and here's a description: retrieves the position of the cursor, of the mouse cursor in screen coordinates. And this function expects that we pass the address of a point structure to this function. And this is how the structure looks like. And along on Windows 32 and also on Windows 64-bit, it's always 32-bit, so it doesn't matter if it's a 32 or if it's a 62-bit Windows, along is always in Windows 32-bit. And yeah, so this point structure, it expects two variables, and here we can see these variables. So it first types struct point, so that's then the name of the structure that we will use, but yeah, we could also use any other name here. Then we have x, res_d, so reserved dword, and then for y also reserved dword, and also here we could use any other name. And then at the end type and struct. And then we have the format variable, and the output of the program looks like this. So at first we have the x, and then we have the x coordinate, so here's x, then the x coordinate, then we have y, and then the y coordinate. And 0x, or we could also just write 10, that's then the line break, so you can see after every output it makes line break. And then finally the null terminator. And then in the BSS section, we need to reserve the memory for our point structure. So then type point, or here any other name, resb, that stands for reserved bytes, and then use this syntax structure name underscore size, because NASM will now calculate the correct size of the structure, and that means we don't need to add the value here by hand. NASM will do that automatically. It will calculate the correct size for us. And then we're here, sub RSP, we know that already. It's for the stack alignment and to reserve the memory for the Windows API functions. And lab1, this is a label. And then later, after the execution of call printf, this program will jump from here back to here, and then it will execute the code again, so it runs in an endless loop. And then in the next instruction here, lia rcx point, there we move the address of the point structure to rcx, or maybe I should explain what a structure is. So here we have a point, and at endpoint is at this address, for example, at address 0, and the first value in the structure here is res as x, so that means x, and it has the size of a d word, and d word has a size of 4 byte, so that means 0x4, and the next value in memory would start here. So that are offsets, but I will make also a video about structures. We'll talk in more detail about that. And then finally we call the GetCursorPos function, and this function, it will then fill our structure with the coordinates. And GetCursorPos, it returns also a value. It's a boolean, so that means it's true or false, 1 or 0. And when the function execution was successful, then it will return the value 1 in the rex register, and otherwise 0. Then we move the address for format to RCX, and then we remove the value from the X coordinate to EDX, to the EDX register. Why EDX? Because we are using here only 32-bit values, so 4-byte values. And this is the syntax to access the structure or the coordinate in the structure. So point, here point, that we have reserved in the BSS segment, plus point dot x, and that is then how we can access this variable. Then remove the value to edx, and then the same, but just for the y variable to r8d. Why r8d? Because r8d that is for the 32-bit values, and the normal r8 that is for 64-bit values, and we know already. So res y is also a d word, and then we call the printf function, and then it goes to the label, and then it jumps back here to the label and then keeps executing the code. And now I will load the program in NASM. And here's the first instruction, subRSP28. And then we will move the address of the structure to RCX. Okay, so here's RCX. And here's a structure. So it's here it's still empty. That is oh, that was wrong. So here you can see 1, 2, 3, 4, and again 1, 2, 3, 4. That is the area where we will write our values, or where GetCursorPos will fill in the values. Then the next example is here, get physical cursor post. So instead of get cursor post, This is now called GetPhysical. This is just how it was, how the function name was resolved. And now pay attention here to the structure. And here we can see the first values. Now we need to read the values in little endian format, so that means we read from right to left. So the first value is 2 FC, and that means x equals 764. And then the next one is just 93. And 93, that is 147. Okay, then we will move the address of format to RCX. So you can see now it has got the address. Then remove the X value to EDX. Here, EDX now. And then remove the address from the Y variable to R8D. And you can see now the value 93. Then we execute printf. So here's the program. And then I will execute the function. And here we can see the output. And then here you can see the jump instruction, and it jumps back. So when I click on jump, and then I press enter, then we can see to which address it jumps. And now it keeps printing the values. And yeah, that's it for this video.